To finish off our discussion of context-free languages, let's look at the properties of this class of languages. Remember, there are two kinds of properties we find useful. One is decision properties, where we tell something about a language or languages in the class, such as whether the language represented by a grammar or PDA is empty. And the other is closure properties, where we prove that some operation, say union, applied to languages in the class, results in another language in the class. First, let's remember that when we talk about a decision property or a closure property for a language class, we're talking about algorithms that take a representation for a language in the class and produces an answer. For the regular languages, we use regular expressions and deterministic finite automata as the representations. Here, for context-free languages, we use the context-free grammar or the pushdown automaton as the representation, whichever makes life easier. And when we use the PDA, we can let acceptance be by final state or empty stack, again, whichever makes life easiest. Here are some questions about context-free languages for which algorithms exist. Given a representation for a context-free language L and a string W, we can determine whether or not W is in L. We can tell whether a representation for a context-free language L generates the empty language. And we can also tell whether this language L is finite or infinite. Unfortunately, many of the things we can decide about regular languages, we cannot decide for context-free languages. For example, we were able to tell whether two regular languages, say represented by DFAs, were the same. We can't tell whether two context-free grammars or two PDAs define the same language. Another thing we cannot tell is whether two context-free languages are disjoint. We say sets are disjoint if their intersection is empty, that is, they have no members in common. We didn't address the question of disjointness for regular languages, but you can tell whether two regular languages are disjoint. We showed regular languages are closed under intersection using the product automaton trick. We also showed that you can tell whether the language of an automaton is empty. These two ideas together give you an algorithm to test whether two regular languages are disjoint. At this point, we have no way to prove that no algorithm for a task exists. That is the job of the theory of Turing machines and decidability, and that will be the next big topic that we address. Now, the emptiness test for context-free languages has already been given in essence. We showed how to eliminate useless symbols, those that participate in no derivation of a terminal string. Take any context-free grammar and see whether or not the start symbol is useless. If so, the language of the grammar is empty, and if not, then not. The membership test for DFAs was really simple. We just simulate the DFA on the string. We can also test whether a terminal string W is generated by a grammar G, but the test is remarkably hard by comparison. We'll assume G is a grammar in Chomsky normal form. If not, we know how to convert the given grammar to CNF, so let's do that as the first step. There's a small matter that when we convert to CNF, we lose the ability to generate the empty string. But if W, the string we want to test, is epsilon, then there is another approach entirely. Apply the algorithm we learned for finding the nullable symbols, those that derive epsilon. See if the start symbol is one of these, and that lets us test membership of the empty string in the language of a context-free grammar. We're going to give an algorithm called CYK. The initials stand for the three people who independently invented the idea: John Koch, Dan Younger, and Tadao Kasami. This algorithm is a great example of a dynamic programming algorithm and worth seeing for that reason alone. The running time of the algorithm is of the order of n cubed, where n is the length of the input string W. Incidentally, there is another algorithm due to J. Early that also runs in time order n cubed, but on an unambiguous grammar, Early's algorithm is faster. It's order n squared. However, the CYK algorithm is much simpler, and as I said, worth studying because it is a model for so many useful dynamic programming algorithms. So that is the one we're going to learn. Here's how the CYK algorithm works. Start with an input string length n. Let a sub I be the symbol in the ith position. We're going to construct a triangular array with short sides each of length n. Each entry in the array is a set of variables of the grammar. The set x sub ij, which will be in position ij, and I is equal to or less than j, is intended to be the set of variables A that derive the substring of the input, starting at position I and ending at position j. That is this. We'll use an induction to fill the table. The induction is on the length of the string derived, which is j minus I plus 1. So we start by computing the entries x sub ii, which is the set of variables that derive the string consisting of the one position ai. From these we can find the xi plus 1s, each of which is the set of variables that derive the string ai followed by ai plus 1. Then we move to the xii plus 2s, which are the sets of variables that derive the strings of length 3, ai plus 1, ai plus 2, and so on. Finally, after we have computed the one set x1n, which represents the entire input, we can ask ourselves whether s is in that set. If so, then s derives a1 through n, and the string w is in the language, and otherwise not. For the basis, we know that the only way to derive a string of length 1 in a CNF grammar is to use a production whose body is a single terminal. So for each I, we can set xii to the set of variables a, such that a goes to ai is a production. For the induction, where j is strictly greater than I, we can compute xij from x's representing two substrings of ai through aj. The first is the substring from ai to ak for some k less than j, and the second is ak plus 1 through aj. Both these strings are of length less than j minus I plus 1, so we have already computed the sets x sub ik and x sub k plus 1j. In order for a variable a to derive ai through aj, there must be some production, say a goes to bc, where b derives ai to ak, and c derives the rest. That is, for each k between I and j minus 1, we look for some b in xik and some c in xk plus 1j, such that bc is the body of an a production. If for any k, b, and c we find such a production, we add a to xij. We're going to do an example of the CYK algorithm. Here's the CNF grammar we'll use, and the input string w will be ABABA. It is of length 5, so we're going to compute sets of variables xij for I less than or equal to j, and I equal to greater than 1, and j less than or equal to 5. That's a triangular array. For the basis, let's see which variables have a production whose body is a. These variables are capital A, has this production, and capital C, which has that production. Thus, if W has the symbol little a in position I, then XII will be AC. We see A in positions 1, 3, and 5 of W, so that explains X11, X33, and X55. For terminal B, we see body B in productions for B and C. That's here and here. Thus, if I is a position of W that holds B, XII will be BC. That explains positions 2 and positions 4. Now we need to compute the 4 entries in the row above. These are the sets of variables that derive substrings of length 2. Here's one example, x12, which is the set of variables that derive the string in the first positions of W, that is, AB. When j is I plus 1, k can only be I. That is, the only way to derive a string of length 2 in a CNF grammar is to use a production where one variable is replaced by two, and each of these variables derives one terminal. So the reason S is in x12 is that A is in x11, B is in x22, and S goes to AB is a production. And the reason B is in x12 is that A is in x11, C is in x22, and B goes to AC is a production. Notice that C can't be in x12 because C derives only strings of length 1. However, A can derive long strings and yet is not in x12. The reason is that the only production A has with a body of two variables is A goes to BC. That's this. In order for A to be in x12, we would need to find B in x11 and C in x22. The latter holds, but B is not in x11. Here are the other three sets for the row corresponding to the substrings of length 2. We'll leave it to you to verify that those are correct. Now let's start computing x13. A string of length 3 can be broken in two different ways, either a string of length 1 followed by a string of length 2 or vice versa. In the first case, k equals 1, and we must combine x11 with x23. x11 has A and C, while x23 has only A. The only bodies we can form from these are AA and CA. But no variable has a production with either of these as the body. Thus k equals 1 gives us nothing. We must also consider k equals 2, where we combine x12 with x33. Now there are four possible bodies, B or S followed by A or C. Of these, only BC is a body of a production of our grammar, and its head is A. Thus, x13 turns out to be just the set containing A. Here are the other two x's for substrings of length 3. There is a pattern to computing these corresponding to the choices of k that we may make for each. We start at the bottom of the column. For example, for x24, that would be x22. And we start going down the diagonal to the right. For x24, that would be x34. So we're going to pair x22 with x34. We then pair them to see what production bodies we can form, and then we move up the column, here in this case to x23, and down the diagonal, in this case, to x44, and we pair these two guys to again see what variables we can form from that one followed by that one. Here's how we compute x14. Starting at the bottom of the column, that is x11, and the top of its diagonal, that is x24. We pair these to see if we can form any production bodies. In this case, we can combine A from x11 and B from x24 to put S, the head of the production with body AB, into x14. Now we move up the column to x12 and down the diagonal to x34, but pairing B or S with B or S doesn't give us any right sides. So we proceed up the column to x13 and down the diagonal to x44, and we pair A with B or C. AC is a body, and it justifies our putting B into x14. Here are the last two entries in the triangular table. x25 turns out to be the set containing A. We'll let you check that one out. And x15 is also A. We get A from x14, which has B, and x55, which has C. BC is a body, and A is its head. Since S is not an x15, we conclude that ABABA is not in the language of the given grammar. We also claim that there is an algorithm to tell whether a context-free language is finite or infinite. We won't give the algorithm in detail, but it is essentially the same as the time-consuming algorithm we gave for regular languages. We use the pumping limit constant n, and as for regular languages, we can show that if a context-free language contains any string of length between n and 2n minus 1, then that string can be pumped and the language is infinite. Otherwise, the language is finite. We're now going to enter the area of closure properties, and for many of the same operations under which the class of regular languages are closed, the context-free languages are also closed. These include the regular expression operations themselves, union, concatenation, and closure, and also reversal, homomorphism, and inverse homomorphism. But unlike the class of regular languages, the class of context-free languages is not closed under intersection or difference. Here's a proof that the union of two context-free languages is a context-free language. Let L and M be the context-free languages, and let them have grammars G and H respectively. We need to rename variables of one of these grammars so no variable is used in both the G and H. The names of the variables don't matter, so we can always do this. The reason it is so important is that we're going to throw the productions from G and H into one pile, and if they had variables in common, we could accidentally use a production from G on a variable from H or vice versa. Note that we do not change the terminals of the grammars. It's okay if they have terminals in common. In fact, we expect that they will have terminals in common. Suppose S1 and S2 are the start symbols of the two grammars after renaming the variables. And we'll build the grammar for L union M by combining all the symbols of the two grammars G and H. That is, the new set of terminals is the union of the terminals of G and H, and the new set of variables is the union of the variables in G and H, plus a new symbol S that is not a symbol of either grammar and will be the start symbol of the new grammar. The new set of productions is the union of the productions of G and H, plus two new productions, S goes to S1 and S goes to S2. All the derivations of the new grammar start with S. And in the first step, this S is replaced by either S1 or S2. If S is replaced by S1, then the entire derivation must be a derivation of G, because we cannot then get any variables of H into our derivation. Similarly, if the first step gives us S2, then the entire derivation is a derivation of H. Thus, the terminal strings derivable from S are exactly those in L if we start with S goes to S1. Union those in M if we start with S goes to S2. That is, the new grammar's language is L union M. The argument that the class of context-free languages is closed under concatenation starts the same way, with grammars G and H for the languages L and M. These grammars are assumed to have no variables in common and to have the start symbols S1 and S2 respectively. Again, we combine the two grammars as we did for union. The only difference is in the productions we use for the new start symbol S. Here there's only one production, S goes to S1 followed by S2. That way all strings derived from S will be a string of L followed by a string of M. That is, the new grammar will generate L concatenated with M. For Kleene star, let's start with the grammar G for the language L. Let this grammar have a start symbol S1. Form a new grammar by adding to G a new start symbol S and the productions S goes to S1S or the empty string. Then a rightmost derivation from S begins by generating 0 or more S1s, that is, it uses this production as many times as it likes, followed by S goes to epsilon. From each of these S1s we can generate exactly the strings in L, so the new grammar generates L star. Reversal is another operation for which it is easy to show closure using grammars. If we have a grammar G for the language L, we form a grammar for L reversed by reversing the bodies of all the productions of G. For example, here is a grammar for the language 0 to the n, 1 to the n. If we reverse the bodies, we get this grammar. It is easy to see that this grammar generates all strings of one or more ones followed by the same number of zeros. That language is the reverse of the language we started with. We're not going to give a proof that this construction works. It is a simple induction on the lengths of derivations in the two grammars. To prove closure of the context-free languages under homomorphism, let's start with a grammar G for a language L and let H be the homomorphism on the terminal symbols of G. Then H of L has a grammar that we can construct by replacing each terminal A in the body of any production of G by the string H of A. So for example, here G is our customary grammar for 0 to the n, 1 to the n. And here's our usual example of a homomorphism. Then H applied to the language of G has a grammar in which the two occurrences of 0 in the productions of G are replaced by AB, and the two occurrences of 1 are replaced by the empty string. Notice that the resulting language is all strings of one or more ABs. It is in fact a regular language, although in general we can only be sure that it will be a context-free language. Next, we take up the fact that context-free languages are closed under inverse homomorphism. While we seem to have done pretty well using a grammar as the representation for context-free languages so far, here we really need the PDA representation. Start with a PDA P that accepts the language L by final state. We'll construct another PDA P prime that accepts H inverse of L, where H is some homomorphism. The big idea is that P prime will simulate P, but P prime needs to apply H to every input symbol it sees, and since H of A may be a long string, P prime has trouble simulating P in one move, and often it cannot do so. So P prime will take it one step at a time. It has a state with two components. The first is the state of P, which is important in the simulation. But the second is a buffer that holds a suffix of what you get by applying H to some one symbol. This buffer allows P prime to use the symbols of H of A one symbol at a time to cause moves of P. Here's a rough sketch of what P prime looks like. As mentioned, its state has two components, the state of P and the buffer. We show input 0011 as an example only. Now P prime can read its first input symbol, 0, and apply H to it. The buffer, which was initially empty, now has the string H of 0. It may be a long string, but its length is finite, so there is only a finite number of states P prime can be in. Now to simulate P, P prime takes the first symbol of H of 0 and simulates P using that as the next input symbol. The simulation could take many moves, as there can be transitions on epsilon input as well as one transition on the symbol itself. However, the symbol is removed from the front of the buffer, so the next time P needs a real input symbol, it gets the second symbol of H of 0. The simulation proceeds in this manner until all symbols of H of 0 are consumed from the buffer. At that point, P prime can apply H to its next input and refill the buffer. To be more precise, the states of P prime are pairs QW, where Q is a state of P, and W is a suffix of H of A for some symbol A. Note that given P and H, there are only a finite number of values of W, and of course P has a finite number of states Q, so P prime also has a finite number of states as is required for any PDA. The stack symbols of P prime are those of P. Moreover, as we shall see, the stack behavior of P prime mimics that of P. And the start state of P prime is Q0 epsilon, that is the start state of P paired with an empty buffer. The input symbols of P prime are those symbols A for which H of A is defined, and the final states of P prime are the final states of P paired with an empty buffer. Now we'll show how P prime simulates P by giving the transition function delta prime for P prime. The first type of transition allows P prime to read an input symbol A, which must not be epsilon, apply H to it, and store it in the buffer. The buffer of P prime must be empty for this to happen, although since P might be able to make moves with epsilon input, P prime is not forced to refill the buffer just because it is empty. It can also make moves without consuming its own input. Formally, delta prime of Q epsilon A and X, this, has one choice. It can remove the A from its input. Again, remember A is not empty. Place H of A in the buffer and leave its stack and state unchanged. Note that h of a might be empty, in which case the buffer remains empty, but it is also possible that the buffer now contains one or more of p's input symbols. P prime also has the option to ignore its own input and simulate p as if p's input were whatever it is in the buffer. Formally, suppose that delta of q, b, and x contains p alpha. Here b may be epsilon, or it may be an input symbol of p. And then for any buffer string of the form bw that is a suffix of h of a for some a, delta prime of q in the buffer bw with no input, this epsilon input, and x on the top of the stack will contain pw alpha. That is, b is consumed from the front of the buffer, the state of p changes according to the given choice of p's move, and the stack of p prime also changes in accordance with that given move. In order to prove that p prime does what we want it to do, that is, accept h inverse of the language of PDAP, we need to do two inductive proofs, one in each direction, of the statement that characterizes the way in which p prime simulates p. We're not going to give the proofs here. The precise statement of p prime simulates p is given in the middle of the slide. It says that p prime goes from its initial ID with input x, that's this, to some ID with state q of p, buffer contents x, w consumed from the input, and alpha on its stack, and that's this, if and only if, well, first of all, p goes from its initial ID with input y, that, to an ID that has state q, input y consumed, and alpha on its stack, that's that. And second, h of w is y, that's what, p consumed, followed by x, which is the thing that p prime still has left in its buffer. Once we have that, we can restrict it to this case where x is empty and q is a final state. It then says that p prime accepts w if and only if p accepts h of w. That is, the language of p prime is h inverse of the language of p. We have not yet addressed intersection. Remember that the regular languages are closed under intersection, and we proved it by running DFAs for the two languages in parallel. But we can't run two PDAs in parallel and still have a PDA. The reason is that the parallel execution of two PDAs requires two separate independent stacks, and a PDA is only allowed to have one stack. That's only an argument that the obvious first try at proving context-free languages are closed under intersection won't work, but the situation is worse. We can see particular context-free languages whose intersection is not a context-free language, so no construction could possibly work. We said that this language, L1, the set of strings with some number of zeros followed by the same number of ones and the same number of twos, is not a context-free language. The pumping lemma gives us an easy proof of that fact. We're not going to do it here, but it's very much like the example of the pumping lemma proof that we did give. But consider L2, the set of strings in 0 star, 1 star, 2 star, that is, strings of zeros followed by some number of ones followed by some number of twos, such that the number of zeros and ones are the same with any number of twos. This language is context-free, and here is a little grammar for it. The job of variable A is to generate zeros followed by an equal number of ones. We've seen this mechanism several times before, and B generates just any number of twos, at least one of them. Now let L3 be the set of strings in 0 star, 1 star, 2 star, with equal numbers of ones and twos and with any number of zeros. This language is also context-free, and the grammar for L3 uses the same ideas as the grammar we just showed for L2. But L1 is the intersection of context-free languages L2 and L3. We can also show that the difference of two context-free languages is not necessarily context-free. In fact, we can prove something surprising. Intersection can be expressed in terms of difference alone. Therefore, if any class of languages is closed under difference, it is also closed under intersection. The argument is that the intersection of any two languages, L and M, regardless of whether they're regular, context-free, or not context-free, is the difference between L and L minus M. That is, suppose X is in L intersect M. Okay, then X is surely not in L minus M, because it's in both L and M, and therefore X is in L and not in L minus M, therefore it is in this expression on the right side. That proves containment in one direction. For the other direction, suppose X is in L minus M. That's this guy here. Then X is in L, and it's not in L minus M. But if X is in L but not in L minus M, it must be that X is also in M. Thus, X is in L intersect M. That proves containment in the other direction, that is, X here implies X there, and that proves the equivalence of these two expressions. Now, suppose the class of context-free languages were closed under difference, and L and M are context-free languages. Then L minus M would be context-free, and so would this guy, L minus M. But we just proved that this expression is the same as L intersect M. Thus, context-free languages would be closed under intersection, but we know they're not, so we know they could not be closed under difference either. We know that the intersection of two context-free languages may not be a context-free language. However, if we intersect a context-free language and a regular language, then we always get a context-free language. The idea is to run a DFA in parallel with a PDA. Since the DFA has no stack, we do not face the problem of trying to simulate two stacks with one that we face if we try to run two PDAs in parallel. Here's the picture of a PDA and a DFA running in parallel. We can combine the states of the two automata to make one state for a new PDA. It manipulates the stack of the original PDA and feeds inputs to both the original PDA and the DFA. It accepts if both the PDA and the DFA accept. To give the construction of the new PDA, let the DFA have a transition function delta A, and the original PDA will have a transition function delta P. States of the new PDA will be pairs. The first component, Q, is a state of the DFA, and the second component, P, is a state of the PDA. Suppose the original PDA has a choice of move from state P and stack symbol X, where A is consumed from the input. That's this. A could be a real symbol or epsilon. The result of the move is that the PDA state becomes R, and X on the stack is replaced by alpha. That's the move. Then the new PDA, whose transition function we call simply delta, given a state with P as the second component, input A, and stack symbol X, that's this, has a choice of move where the new state has second component R. The first component is what you get by having the DFA make a transition from state Q with input A. That's delta A of Q and A. Note that A could be epsilon here, in which case delta A of QA is just Q, or it could be a real symbol in which delta A of QA is something else. Finally, this choice of move replaces X by alpha on the stack, just as the original PDA did. The final states of the new PDA are the pairs QP, such that Q and P are final states of their respective automata. And the initial state of the new PDA is the pair consisting of the initial states of both automata. We need to prove a pair of inductions on the number of moves made by each PDA. These inductions say that the new PDA started in its initial state with input W, this, consumes the input and enters an ID with state QP, and stack alpha, having consumed the input. And that happens if and only if the original PDA goes from its initial ID with input W to the ID with the same state P and alpha on the stack. And of course the DFA goes from its initial state on input W to the state Q. We'll skip the details as the proofs are not too hard.